That's Cinco de Mayo.
So
We're already trapped inside. We might as well do our final.
I mean, it could be Monday. I just thought Tuesday.
No, I'm saying we're already trapped inside. A final is great because then you can celebrate with tacos afterwards.
There you go. And a little tequila.
Yeah.
All right. Okay. Any other questions or comments about anything? So basically now we're done with pre-calculus algebra, and we're done with trigonometry, and we're going to start today on limits. I guess there's nothing else for me to say. Let me just pull up my PowerPoint. Hold on, Chris. You need to get good internet. I don't know how you're going to do it, Chris. I really don't. But if the internet dies on you that day, that is not an excused absence. You've got to get some internet that works. So I don't know what to do for you. Do you have any ideas? Because I don't have any ideas. My only responsibility is to give you the test. Your responsibility is to be on the other end of some good internet. I don't know what you're saying to me, but I can't help you. Like, all I have is online. Like, I don't have another option. So the only option I can give you is online. And since that's my only option, you've got to come up with the other side of it. And I know I shouldn't send you out anywhere, but maybe you have a relative that has good internet that you can go sit at their house, secluded in a room somewhere. But I don't really know what else to say. You have 3 weeks to figure it out. But you also have to take a quiz next Monday, and a makeup test on the Monday after that. So you've got to get some reliable, internet. All right, let me get the PowerPoint. All right. So here we go. All right, so today's lecture is going to be a little different than you're used to, because this is now calculus we're talking about, and there's some things you need to understand. It's not just me putting a problem up basically and solving it. There's some underlying understanding that you're going to have here. We're going to go through some definitions and what things mean. Okay, so let me begin. And ask a lot of questions. So here's my first definition. Suppose f of x is defined when x is near a number a. Okay, so let me do this. Let me draw a graph so that I can draw something to basically go over what this definition is. So let's say I have some graph, whatever my graph is. Okay, there's my graph. So obviously this is f of x, this is the y-axis, and here's x. Now suppose f of x is defined when x is near a number a. So let's call this a. And we have so let's say a equals 1. Now we have some x near 1. So far, are you understanding what I'm saying? So it says this means f is defined on some open interval. So let's say I have this open interval around a, and that contains a. Except it says except possibly at a itself. So what if I put an open circle there? So now I have this function that's defined on this open interval that contains a, except it's not actually defined at a. Okay? And it says we write the limit, and this would be L. This says the limit of f of x as x approaches a is equal to L. So we can make these values of f of x arbitrarily close to L, but by how we're going to do it is we're going to get x's close to a on either side, even if it doesn't actually equal a itself. So that's kind of my explanation. We're going to go over a lot more things about it, but do you have some understanding of what this says? Or does anybody have a question? Yes? Okay.
I kind of have a question. So in the homework, you gave us like an f of x, and I remember when you did the graph, it was as if 5, I remember was the example, was the open circle. So any number of value of x we plugged in, we wouldn't get the value of L, right? Is that what we're looking for, L?
So let's just look at what I just said here, okay? So do you understand what I said here? We're going to go through a lot of slides.
Yeah, I'm just trying to relate it.
It's not the end of the lecture.
Yeah.
Huh?
I was just trying to relate it to like what we saw earlier.
I'd have to look at, I'd have to look at the actual worksheet that you're talking about.
Okay, you're fine.
Okay, if you want me to, I'll pick it up. I'll bring it up.
Greenberg, so is the limit the whole line system, like this whole, like the limit of f of x, is it like the whole line system going into the open circle?
No, so the limit will be one value. So how about if you just hold on, like, you know what, let's hold on to it for a second. We may come back to this slide for more clarification, okay? Let's go on and see if I go through the next few slides, if it helps you understand what we just said, okay? If not, I'll come back, I promise. So we're going to look at a table of values. So let's say we have this graph. We have this function, f of x equals the square root of x minus 1 over x minus 1. And we want to know what is the limit as x gets closer and closer to or approaches 1 of the square root of x minus 1 over x minus 1. So I'm not being asked what is f of 1, because f of 1 is actually undefined, isn't it? Because I would have 0 over 0, which is undefined. Is everybody clear about that?
Yes.
Okay, good. So what's happening here is this is not the graph of this function. I don't know exactly what the graph of this function looks like, honestly. But let's say at 1, it's, I don't know, let's say it's an asymptote. I don't know if it's an asymptote or an open circle. I don't know. I'd have to figure it out. I don't know. I really would have to. But let's say it's an asymptote. We can't go through 1. So let's say I have this graph, and let's say it looks like, no, it can't look like that. Hold on. Let me make something. Let's say I have a graph that looks like this. Here's 1. We definitely have an open circle here. And here is our limit, okay? So as we get closer and closer to 1, what we want to know is what value f of x equals, okay? I can't plug in 1, but what I can do is I can plug in 0.9. And when I plug in 0.9, I get 0.513. So that's like right here. I have 0.513. So again, this graph is wrong because it should be above the limit. Here, let's do this. Okay. So, and then when I plug in 0.99, I get 0.501. And when I plug in 0.999, I get 0.5001. So like the closer I'm getting to 1, notice it's getting closer to 1/2 or 0.5. And then we look at it from the other side, and the closer I get to 1 on the upper side of 1, notice here it's getting closer and closer to 0.5. So I can say the limit equals 0.5. Is that understood? So here's my 1, and what I'm doing is I'm looking at this open interval around 1, and I want to know what value this function has at 1, but I can't just plug in 1, so I have to do some other things. Does that make sense? Hello?
Yes.
Okay, good. Good. So now we're going to talk about one-sided limits. So a one-sided limit, let me draw another graph. So if I have a graph, let's say it looks like this.
Can you go back to that last slide? I just want to see that equation that you had.
Sure. Hold on.
Okay, thank you. I got it now.
Okay, perfect. So let's say I have a graph and it looks like this, and this is A right here, okay? And let's read the definition. Suppose f is defined for all x near A, so it's defined for all x in that open interval. But for the right-sided limit, we're looking at just things where x is greater than, so we're only looking at from here on. So this is a right-sided limit because if I'm looking around 1, what I want to do is look to the right and see what value this limit is. So let's read the definition. Suppose f is defined for all x near A with x greater than A, so only x is greater. If f of x is arbitrarily close to L for all x that's close to A, then we have the limit. And notice this right here, this plus sign right here, that's not meaning a positive A. It means I'm looking at the value of A, but to the right of it. As opposed to here, we have a negative sign. And what I'm doing is I'm looking at all the values on this function to the left of A. Okay? And we're looking to see what values are happening. Okay? So let's see if I can give you some. Here, let me draw another graph that maybe will help understand this. Okay, so let me make it. Let's do it again. So here's my function. So I'll call this 4, and I'll call this 1, and I'll call this -2. Here's my function. Okay? And this is a piecewise function. And if I want to know what is the limit as x approaches A from the right of f of x, and here A is 1, so instead of writing A, actually here I'm going to write on the plus side of f of x. Well, here, what would you say that would be equal to?
That'd be equal to 4?
No, because what I'm doing here is, let me get up another column. So what I'm doing here is this is from the right. So that means I'm coming into this. It means I'm coming at this graph. I'm coming in. There we go. I'm coming in to this 1 from the right-hand side. So I'm literally coming down this graph, and I'm getting closer and closer to 1 from the, yes, Chris, exactly. It's getting closer and closer to -2. Does that make sense? And if I ask, what's the limit as x approaches 1 from the left of f of x, what does that equal? So now I'm coming at this value from the left. The left is over here, right? So I'm coming along this line, and what is the limit on that side?
4.
4. So these are right-sided limits. I'm sorry, these are one-sided limits. We have right side and left side. If I want to know what the limit as x approaches 1 of f of x equals, for this, it's undefined. It doesn't exist. It doesn't exist because they both go to 2 separate numbers. Is that clear?
Excuse me?
Yes.
I get how you got 2 for the...
Alian, can you get closer to your mic?
is this better?
A little bit. It'd be better if you can get a little bit closer.
Is this better?
Way better.
Okay. So I understand how you got -2 for the x for the right-sided limit, but I'm not sure how you got for the left.
You're not sure how I got 4?
Yeah.
What I'm looking at is I'm looking at the y value, because I'm looking at what is the f of x, and f of x is the same as y, right?
Oh, okay.
Make sense?
And you said it was undefined because of that.
It's undefined. So if I come from the right, it's equal to -2. If I come from the left, it's equal to 4. But if I ask you what is the limit, and I'm not giving you one side or the other, it doesn't exist because which one would you pick?
Okay, thank
It's not
you.
random. Does that make sense?
Yeah, that makes sense.
Right, good. Is everybody with me? Are there any more questions? Ask a lot of questions. I'm good with this. I like the questions.
Yeah. So question. So if you ever have two-sided limits like this with 2 values, it's always going to be like the NE or no limit, right?
Yeah, it's a DNE, does not exist.
Does not exist. I thought that was one with a parentheses.
Yeah, no, it's actually a DNE. It's really hard. They have this annotation tool, which makes it really hard because every time I do something, it moves things around. But
Okay.
okay, but yeah. So does that make sense now?
Yes.
Okay. All right, so let's continue. So here we have 2 graphs. They're both of the same function. The one on the left isn't actually correct because we should have a hole at x equals 2, right? Because when x equals 2, we have 0 over 0, which is undefined.
Ah, I see. So we're looking for the undefined part of the graph.
Yeah, so here I could say, what's the limit as x approaches 2? And I could say, let's look at it from the right. Okay, so from the right, what's the limit as x approaches 2?
It does not exist
Why not?
because there's a hole there.
But it does exist. Because remember, okay, so here was what we're going to do. We're going to go back to that original slide, and notice it says, is defined on some open interval that contains A, or the x value, except possibly at A itself. So it doesn't actually have to be defined exactly at A. It doesn't have to be defined exactly at 1, because don't I know what the value is there? If that circle was colored in, wouldn't I know what it is?
Yeah.
Right? So what I'm saying is, sorry, I've got something happening here. So if I were to say, as I come in from the right, I'm getting closer and closer to 3, aren't I?
Mhm.
And then if I say, what's the limit of x as x approaches 2 from the left, what would that value be, Joey?
Would it still be approaching 3?
It would. Do you see that?
Yeah.
So because it's approaching the same value from both sides, I could say that the limit as x approaches 2 of f of x, and now notice I didn't have to put from a side, it's equal to 3, because both from the right and the left, it's approaching the same value.
Okay, that makes more sense.
Okay, good, good. Is everybody with me? Is there any more questions? Okay.
Wait, Ms. Greenberg. So
Yes.
I'm just confused on. So I see this graph. You said this time the limit does exist. You said, right?
It does, because it's equal to 3 from the right, and it's equal to 3 from the left. So that means that the limit, the two-sided limit, exists, and it equals 3.
So a limit won't exist if there's like two one-sided. You're saying?
If you take two one-sided limits, so one
And
from
they
the right,
don't
one from the left,
match up.
and they equal different values,
Then it does not exist.
right. But here they equal the same value. So the one that didn't have the same values were, right?
The one from the last slide you did.
Yeah, this one, right? Because I'm going from the right, it's equal to -2. From the left, it's equal to 4. So there's no actual limit. There's only one-sided limit.
Okay.
Here, this is a two-sided limit, so the limit, period, exists. You can say the limit equals 3, which also implies that the right side and the left side also equal 3. Right?
Yeah, I understand it now.
Okay, perfect. And that's exactly what this says. So relationship between one-sided and two-sided limits. Assume f is defined for all x near a, except possibly at a. Then the limit of f of x as x approaches a equals L, if and only if from the right it equals L and from the left it equals L. Okay, so that's exactly what we just said. Here it is in the form of a definition. Okay? Okay. So now if I say here, what's the limit? What's the limit as x approaches 2 from the left? Oh, this is g of x. What would you say that's equal to? Yeah, Jack.
4?
4. Good. And what if I say I have the limit as x approaches 2 from the right of g of x?
Would it still be 1? I mean, would it be 1?
It would be 1. So do
Yeah.
I have a limit as x approaches 2 of g of x?
No.
No, it does not exist. Is that making some sense now?
Yeah.
Y'all starting to catch on? Okay, good. Awesome. So here we have another chart. And if you notice, what I'm doing is I'm saying I'm getting closer and closer. And here I have right-hand and left-hand side. So here I have 0.9. My value is equal to 1.9. And when it's 1.1, it's equal to 2.1. And when it's equal to 0.99, then we get 1.99, 1.01, 2.01. Can you see that the closer I get to 1 from both sides, the closer I'm getting to 2. So the answer is equal to 2. And algebraically, there's something else I can do, because remember, we said, even when we were doing rational functions, we said if we have x squared minus 1 over x minus 1, do we have an asymptote here? Do we have an asymptote for this function?
Yes. Wait.
Don't.
No, because it's factored out when you do the.
Right. Remember, you always, before you figure out if you have asymptotes, what you have to do is simplify. So I can say that this equals x plus 1 times x minus 1 over x minus 1, right? And then I can cancel those, which gives me x plus 1. Now, that's true everywhere but exactly at 1, right?
Yes.
There's a hole there at 1. But with limits, we don't care if there's a hole, because we're not actually talking about what is the value at that point. We're actually talking about what is the value as we approach that point from left and right. See the difference?
Yeah.
So this would equal 2. So this is how you do it algebraically, and this is how you would do it with a table.
Ms. Greenberg,
Yes, sir.
is there like a specific reason why, like on this table, like there's 0.9, then 1.1, then it goes back down to 0.99?
Yeah, this is coming at, so
Oh,
this
it's just
graph,
like,
this graph would basically look like, kind of like this, with a hole here at 1, right?
okay, it was just like messing with me because like the values were like out of order.
Well, they're just saying, let's take a point over here, and then let's take a point over here, and
Yeah,
then let's
I
get
get it.
closer, and then we'll get closer, and we're just getting closer and closer to that point at 1. We're just
Okay.
coming at it from both sides, and we're seeing that from both sides, it's approaching the exact same number.
Why are we using like small decimal points instead of using whole real numbers?
Because you wouldn't be able to see where it's getting closer and closer to. If you use 3, 2, 1, you can't use 1. So if I plug in 3, I'm not getting close to that value, am I?
Okay.
So what you're doing, obviously you would need a calculator to do this. So
We're just trying
this
to
is not
find
something
the
you do in
limit
your head.
before it touches the vertical asymptote.
There's not an asymptote here. There's a hole.
All right.
Okay?
Yeah, the fact that can't equal to 1, I just assumed I include a vertical asymptote there.
It's not an asymptote. If you remember, hold on a second. Chris, I missed your text. Just retype it and I'll catch it. Just copy and paste it back in, because it shows up for a short amount of time. I just didn't have a chance to read it. Hold on one second, Logan. At that point, it terminates into. Yeah, it's not a continuous function, but that's not what we're talking about. We're not talking about continuity. We're talking about limits. Strictly, we're talking about limits. Okay, and what we're talking about is this function approaching a value at a point? Not necessarily does the point exist, but if I come at this point from both the left and the right, am I getting closer and closer to one value?
Okay.
Okay, and yeah, Chris, if I plugged in 1, I would get 0 over 0, which doesn't exist. But if you remember back to rational functions, see, when I talk about the fact that everything we've done in this class is important, I kind of mean it, because if you can understand rational functions, that remember we had to, before we looked to see if we had asymptotes, we had to look to see if we could simplify. Because if we can simplify, we didn't have an asymptote, we just had a hole. Okay?
Okay.
All right, so now we're going to talk about infinite limits. So infinite limits have to do with things that do have asymptotes, because now, if I want to know what is the limit as x approaches pi over 2, let's just say of the secant of x, well, it's an asymptote, right? So it doesn't have a limit. But what I want to do is I want to say, well, let's look at it from the right-hand side. So from the right side, I'm coming across this graph right here, because this is just right of pi over 2, right? And notice what's happening here is it's going to negative infinity. Does everybody see that? And if I say the limit as x approaches pi over 2 from the left of secant of x, that equals positive infinity. So I can say that the limit does not exist. Is that clear? Okay, that's a yes. And the same is true for tangent. Okay, perfect. So infinite limits, I'm not going to read you all of this because it's really just what I said. So we're just going to move on to the next one. Here, now notice here, the limit as x approaches -1 of f of x, it's equal to minus infinity because both from the left and right, it equals, they go to negative infinity. And here it's same as true, they both go to positive infinity. So I can say the limit exists and it's positive infinity. Is this starting to kind of come together a little? Does anybody have any questions? Okay. So now we're going to say, if I'm given two limits, and the limit of this function equals infinity, of f of x equals infinity at some value c, and g of x at the same value c has a finite limit called L, if I add them or subtract them, I'm always going to have infinity as my answer, aren't I? So if I said here that the limit is less than 0, then this would equal negative infinity, wouldn't it?
Yes, I think I understand that.
Okay, good. But now here's one thing that's very interesting. If it equals 0, it's called an indeterminate form, which basically means I don't know the answer. So 0 times infinity is not 0 necessarily. I know that kind of blows up all the things you've always been told about anything times 0 is 0, and that's true of any finite number. But infinity times 0 is not necessarily 0. You will learn how to deal with that in calculus. We're not going to do that here, okay? And then the quotient basically says if I divide, so here I have, notice for this quotient, I have the limit of g of x over the limit of f of x. And why is it that they're saying that equals 0?
Because infinity divided by 0 does equal 0?
No, because I don't have infinity divided by 0, do I?
No, you have L divided by infinity.
So what happens as for any function as the denominator gets bigger and bigger?
As the denominator gets bigger?
So we have 1/2, 1/3, 1/10. So the bigger
Smaller.
the denominator gets, what happens to the fraction?
The smaller.
It gets smaller and smaller.
Mhm.
So 1/infinity, which obviously is not something I can normally write, that's going to always equal 0, isn't it?
Mhm. Yeah. Okay.
Even a billion over infinity is still 0.
Yeah.
So it doesn't really matter. Any finite number over infinity is always 0.
Okay.
And that's what that says. Okay?
Can you just go over the sum and products one more time?
Yeah, so let's say I have 5 plus infinity. What's that going to equal?
Infinity still?
Right. What if I have infinity minus 5?
Still going to be infinite?
Right, that's what those two,
Okay.
that's what this says.
Okay.
What if I have 5 times infinity?
Infinity.
That's what the product
Okay.
says.
Okay.
All right?
Yeah.
Everybody's good so far? All right, let's move on. So let's find, I'm not going to do the top one, but I am going to do this. Yes, exactly, Chris, you're right. So if I want to find the limit as x approaches 4 from the left side, okay, does anybody have any ideas how I would do this? First of all, do I have, when I plug in 4, I notice I get 16 over 0, which is undefined, right?
Yes.
So is that an asymptote or a whole?
That's a whole.
How do you know it's a whole?
Because the limit isn't always defined as the whole, like the asymptote.
No. So how do you tell, don't worry about limits. How do you tell if you have a whole or an asymptote? It's not a limit question. It's a graphing rational functions question. When we talked about rational functions, we talked about this. What's the difference between a whole, and I'm not talking about visually, I'm talking about what is the difference between a whole and an asymptote? I'm going to wait till somebody answers that. So I'm going to chill.
Oof.
Anybody knows?
Would it be that an asymptote can't be a value?
A whole can't be a value either. They're both undefined at that point. So this is what an asymptote looks like. Let's say this is my graph, right? And this is what a whole looks like, right? How do I tell algebraically whether I have an asymptote or a whole? Nobody knows?
Well, we were told that holes cancel.
Holes don't cancel, but it's like,
No, like you can cancel them out from the equation, and that's how you know it's a hole and not an asymptote.
right. If you cancel things, like, for example, let's say I have this equation at the top, right? Well, I didn't actually, I shouldn't, like, wait, I'm not going to do that. So this has an asymptote because if I plug in 1, if I plug in 1 here, I can't cancel it. And if I plug in 0, I can't cancel it. Those are two asymptotes. But notice, if I have x squared minus 1 over x plus 1, this is equal to x plus 1 times x minus 1 over x plus 1, right? Do I have an asymptote at -1? What happens when x equals -1?
You fall in a hole.
I fall in a hole because I can cancel these. And when I cancel them, I actually create a hole, not an asymptote, because notice I don't have a denominator. Is that clear?
Yes.
Who answered me? That was Jax? Okay, somebody besides Jax. Thank you, Jax, but somebody besides Jax.
Are you saying that? Are you saying that when x is not equal to -1, we have a hole?
When x is equal, there's a hole at -1.
Yeah. Oh, when x is equal to -1, it's a hole.
That's a hole. It's not an asymptote.
Okay.
Do you see why?
Yeah.
Why?
Because the whole, you can't get the value with the whole, but other than that, there's solutions with x plus
Yeah, but
1.
that's not exact. So Kurt, thank you, but I want this to be very clear, and I don't think it's very clear yet because everybody should be able to answer this question easily when it's clear. Okay, so do y'all see? Yeah, but that's not exactly it either, Chris. So here, I'm going to erase everything here. Started. I wasted way too much. So if I have f of x equals x squared minus 1 over x plus 1, okay? So right now, it's undefined at -1. Does everybody understand that?
Yeah.
Yes? No.
Yes.
It's undefined at -1, okay? But I can change this into x plus 1 times x minus 1 over x plus 1, right?
Correct.
Now, when x is not equal to -1, I can cancel out the x plus 1s, right?
Mhm.
And what do I get? I just get x minus 1. Yes?
Mhm.
Yeah.
Now, does x minus 1 have an asymptote? Is there an asymptote anywhere around x minus 1?
What? Yeah, because okay, so an asymptote is anything that makes the function undefined.
Right.
So
So -1, if that would also be a vertical asymptote.
No, because if I plug in -1, I get -1 minus 1.
Oh, so then no, yeah,
equals
you're good then.
-2. Don't I? If I plug in x equals -1, after I've simplified, don't I get -2?
Yes.
So I don't have an asymptote because I just took the asymptote away.
Okay.
There's no asymptote. When I can simplify a function, then I plug in a value after that. It means I didn't have an asymptote. It meant I have a hole. It's just not defined at -1, but it's defined everywhere else. Okay? But at -1, it's just not defined. We just make a hole. However, let's look at this function right here, the one that's given on this paper, on this screen. Okay, this one. Does the top one, does this have an asymptote?
it would, right?
It would have actually 2 asymptotes. Can I simplify that? Is there anything I can cancel?
No.
So do you see what I'm saying? So this has 2 asymptotes. I can't simplify anything, so I can't get rid of anything in the denominator.
Mhm.
Does that make sense?
Yes.
How about this one? Can I cancel anything on the second one?
Could you like square root all of it?
I could, but first of all, it would change the values. And second of all, what's the square root of x squared minus 16?
Oh, you Oh, I was thinking that you just, I was thinking of doing each value. My bad.
No, you can't do each value. So I can't really simplify that. Okay? So that's not going to help me because this makes me think I have an asymptote. Since I can't simplify it, I have an asymptote at 4, don't I?
Mm-hmm.
Okay, good. So now, how do I find the limit? I know I have an asymptote, not a home. Okay? Well, I want to come in, I'm looking at 4 from the left side, aren't I? From the negative side. That's what that negative over the 4 means. So how about if I just pick a number like, let's let x, okay, huh? Yeah, I'm not right. Here we go. Let's let x equal, how about 3.9? Okay, that's kind of close, but not there, right?
Yeah.
So, but really, since I know it's an asymptote, it's either going to positive infinity or it's going to negative infinity because that's what asymptotes do. It forces the function to positive or negative infinity, doesn't it?
Yeah. Okay. That makes a lot more sense. Okay.
Okay, good. So if I plug in x equals 3.9 here, I don't care what the value is. I know it's positive. Wait, hold on. My computer's doing weird things. Maybe I'm doing it. So I can say when I plug it into the numerator, it's going to be a positive number, right? 3.9 squared is a positive number.
Mm-hmm.
And then 3.9 squared again, I know it's a positive number, and I know it's less than 16 because it's less than 4, right?
Mm-hmm.
So a number less than 16 minus 16 is going to be a negative value, isn't it?
Correct.
So since it's going to be a negative value, I can't put it on the screen. Things are going weird. There we go. This has got to be equal to a negative number, doesn't it? And since it's equal to a negative number, and I know it's an asymptote, this limit is going to equal negative infinity. Negative equals negative infinity. The limit for this, for that function, is negative infinity. Is that clear?
Yeah. I believe so, yeah.
Okay, good. So here we have another case, and we have a graph, but we can see that at 1, the limit is going to equal positive infinity because both of these go to positive infinity. And we can say here that the limit as x approaches 3 from the left side is equal to negative infinity, and from the right side is equal to positive infinity. So if I asked you the limit as x approaches 3 of g of x, what would you say it equals?
Does not exist.
It doesn't exist, exactly. Starting to make a little bit of sense?
Yeah. These are easier. Yeah.
Okay. Okay. So now we're almost there, guys. We're just going to talk about a couple of techniques for computing limits. Okay. So first, here are all the limit laws. They should make sense. If you have two functions that approach some value, if I add them together, I just add their limits together. Same as if I subtract them, I subtract them. If I multiply, I multiply them. If it's a constant times the limit of that function, it's just the limit of that function times the constant. And if I divide them, again, I divide them. Okay, so all of these should make sense to you. I'll just give you a minute to look over any of them and see if any of them don't feel Like you don't understand why that would work. So I'll just give you like a minute. Just tell me if you have a question about any of these rules.
Ms. Greenberg?
Yes.
So I think I get 1 through 3. I
Okay.
think it's just 4. So can
Okay.
you, like the
Yeah.
constant multiple?
Yeah, so let's say I have f of x. So we'll say the limit as x approaches 1 of, instead of saying f of x, x plus, okay? Well, we can see that's equal to 2, right? I just plug in 1, I get 2.
Yes.
Does that make sense? Okay, good. Well, what if I say the limit as x approaches 1 of 3 times x plus 1? Well, that's going to be equal to 3 times 2. And
Okay,
also,
because it's the constant multiple. Okay.
yeah, and also because that 3 has no x in it, I can also say that's equal to 3 times the limit as x approaches 1 of x plus 1, which is equal to 3, again, times 2.
Okay, wow. Okay, that's actually, okay. That makes sense.
Because this 3 is really not being affected by the x going to 1. It doesn't really matter.
Yeah, it's more approaching about the limit. Okay.
Yes, about where x is, not about where some constant is.
Okay. I'm going to write that down real quick. Yep.
Yeah, sure.
All right.
So do the rest make sense? Yeah. So we're find the limit and add the values. Yeah, you just want to, like the limit, like let's say I have the limit as x approaches 1 of x times y. Now, y has nothing to do with x, does it? I can say that's equal to y times the limit as x approaches 1 of x.
Yep.
Because I'm not that my limit as x approaches 1 is not affecting y at all.
Mhm. It's about the position. Okay.
Okay. Should I move on?
Yeah. I understand that.
Okay, perfect. So limits of polynomials can always be found by substitution. Substitution meaning I just plug in my value, just like I just did here. X plus 1 is a polynomial. It's continuous. Remember, I don't know if you remember, but we went through that polynomials are always smooth and continuous.
Mhm.
So because they're smooth and continuous, they have a value everywhere. So I can just plug in my numbers. That's what this is basically saying. Okay? So no matter what it is, I can always plug in a value. Is that clear?
Yes.
Okay. Now, if I have rational functions, again, I can just substitute. I can just always plug in my value. The only time I have to be concerned is when my denominator equals 0. Then I have to do some work, right? But otherwise, I can use substitution. Does that make sense? Do you want me to give you an example?
Yes.
Example or make sense?
Yeah, example.
Okay, yeah. So a rational function could be something like, and only write something. So I have the limit. So I have the limit. Nope. Maybe my pen is ready for something. The limit as x approaches 1 of x plus 2 So now the denominator doesn't equal 0, does it?
No.
So I can just plug in my numbers, is what I'm saying. I can say this equals 3, 2. So I can just use substitution. Because my denominator is not 0.
Okay, that makes sense. That's easier.
Okay, good.
Okay. As long as the denominator doesn't equal 0, you can just plug in that constant.
Yes.
Okay,
Yes,
that's
because
simple.
I have a value. Okay.
Yeah. Okay. Okay.
Sorry. Just we'll do some other problems.
You're good.
Okay, good. So this one, my guess, let's do it. I can simplify. So I can factor this to x plus 2 times x minus 1 over x times x minus 1, right? Which means I can cancel these out, which means I have a hole at 1, which is what this is showing, is that I have a hole at 1, and I have an asymptote at 0. Is that clear? Because this really just equals x plus 2 over x when x is not equal to 1, right? But the limit doesn't have anything to do with what happens exactly at that value. We're talking about the limit as two values as x approaches a certain value. It doesn't say as x equals that value, right?
Right.
So does that mean the limit equals 0.9 and 1.1?
I don't know where you get that value from. How'd you get that value?
Just looking at the problem, if x doesn't equal 1, but the limit's near that, I just thought those were the two numbers.
Well, no, but now I don't have a 0 anymore, do I? Now there's no 0. So if I talk about the limit as x approaches 1 of x plus 2 over x, well, that equals 3 over 1, which equals 3, which is what we're saying the limit equals for this function. It equals 3. Here's my limit. Here's when x equals 1, my L equals 3. Yes?
Okay.
No? Yeah? All right. So if I ask what is the limit, can you all see that if I ask from the limit from the left, let's say I didn't have this graph, okay, and I just had this function. Well, I know the limit as x approaches 1 on the plus side, well, that's going to be, let's make it, yeah, that's okay. That's this one, right? That's the bottom one, because that's x is greater than 1. So that's what this is asking me. Well, okay, I have this function, the square root of x minus 1. But what I want to know is what happens as I get closer and closer to 1 from that side. And what I'm going to do is I'm just going to plug in 1 for x. And it's going to be 0, isn't it? And then for the left, I'm going to use the top function. And when I plug in 1 to the top function, I get 2, which is why I get the limit as x approaches 1 from the left of f of x equals 2. Yes?
That's easy, yep.
Okay, good. Okay, so first step when you're trying to do limits is always try to just substitute, put in the value. Okay? If it doesn't work because you have 0 in the denominator, then you go to the second, which is dividing out technique, or let's call it simplifying technique. Okay? Not simply. Simplify. Okay, so you simplify and look at the answer look at the problem here at the bottom. And what we're doing is we're simplifying. We're factoring, we're canceling. When I get to the point, so I canceled out x minus 5, and I end up with 1 over x plus 5. I plug in 5, I get 1/10. I'm done. Does that make sense?
Yes.
Because I couldn't just plug in 5, I'd end up with 0 over 0. 0 over 0 is the bigger problem, okay? So we've already kind of talked about this technique. So here, again, I plug in 1, I get 0 over 0. So my first step is always substitute. I plug in 1, no good. I'm going to go to my second step, which is simplify. Okay? And then I would have the limit as x approaches 1 of x minus 1 over x plus 1 times x minus 1. I cancel these out. I get 1 over x plus 1, which equals 1/2. Is that clear? And notice, if you notice, I keep writing the limit. Do not get lazy and stop writing limit. It's just a couple of letters. Write that every time. It's like you wouldn't say the square root of x squared equals x squared. You don't just drop things just because you feel like it. Until you evaluate it, you keep them going. You keep this limit on every single equation until you're done, okay? Until you have evaluated it. Is that clear?
Yes.
Okay. Now we have one more thing, which is rationalizing. So when you rationalize, you're not always rationalizing the denominator. Notice for this example, when I plug in 0, I get 1 minus 1 over, which is 0 over 0, right? If we just start here, this is 0, right? So first step is I plug it in, no good. There's nothing I can do here to simplify because I can't factor anything. So again, there's nothing for me to do. So what I'm going to do is I'm going to try to rationalize the numerator. And when I go to rationalize the numerator, notice what I do is multiply the numerator by its conjugate. And when I do that, I get the square, it becomes the difference of squares. So I get the square root of x plus 1 squared minus 1 squared, which gives me this equation. Is everybody with me till the end of the first line?
Yes.
Good. And then again, these cancel, and I get x over x times the square root of x plus 1 plus 1. And then I can cancel my x's, which gives me the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And now, let's plug in my 0. When I plug in my 0, I get 1/2. Okay? So let's do an example. Who wants to do this one? Somebody who hasn't been talking with us whole time. So, who's here? Gio, pick somebody.
Sorry, my mic was muted.
Oh, no problem. Any name.
Michael.
Michael who?
Lou.
Who? Okay, Michael, perfect. Okay, Michael, me and you. Let's see if we can do this.
Okay. So,
So what's the first thing I would do?
you would want to substitute. That's the first
I
step.
want to substitute, yeah. Because if it works, it's always the easiest, right?
Mm-hmm.
So I plug in 0 and I get 3 minus 3, which is 0 over 0, no good.
No good.
Then I try to simplify, but
Yeah.
I don't know how to simplify this, right?
Yeah, no.
Okay, so then the next step I'm going to do is I'm going to use some of my techniques, another technique. So what technique are we going to use here?
You would want to multiply it by the conjugate.
Perfect. What's my conjugate?
Square root of x squared plus 9 plus 3.
Perfect. Excellent. Okay, now I have the limit as x approaches 0. And what do I have in my numerator when I multiply?
The numerator would be x squared plus 9 and then is that minus 9?
Yes. So let me just stop you there because you're right. Does anybody not understand how we got this? Okay, good. Onward. And then the denominator, we just said x squared times the square root of x squared plus 9 plus 3, right?
Yeah.
And then 9 minus 9 is 0.
Mm-hmm.
And then what do I do next?
You can cancel out the x squared.
I can cancel out the x squared, and then I have the limit as x approaches 0 of 1 over the square root of x squared plus 9 plus 3, and then what do I do?
And then you can, this is where you would want to plug in 0.
Yeah, now I just want to plug in 0 and see if it works. If it doesn't, I might have to think of something else, right?
Yeah.
So if I plug in 0, I get 1.
The negative number or a positive number of 3, because it looks like the denominator says square root of x squared plus 9 plus 3. Shouldn't it be minus?
Right. No, it's plus 3 because there it is right there.
All right. I thought you were just multiplying that by negative 3, so that's where I got the idea.
No, I'm not multiplying it by negative 3. I'm doing this times this, and these are conjugates. Okay?
All right, so x squared plus 9 minus and x times 20. Okay, I don't want to babble on forever. Go on.
Yeah, makes sense?
Yeah, I think so.
Okay, good. Good. Some of it, you know, when you start doing the homework in the LA worksheet, that's when some of this should become more clear. Does anybody have any other questions about what we've gone over today? Because I'm gonna end this then, and then I'm gonna come back into the main room. So, on. All right. So now, here's what we're gonna do next. We're gonna do the LA time. But I'm gonna, first of all, I want to know, is anybody not interested in doing LA time? If you're not, just go. Leon told me he has office hours right after this class. So if Leon is your LA, you don't want to stay for LA time right now, you can go to Leon's office hours right now. But only leave if you're going to go and you're in Leon's class. And if you don't care about meeting with somebody, then you can just go. Otherwise, stay with me.
Ms. Greenberg, I have a question.
Yes.
If you're trying to find the office hours for the LAs, is it still the same ones that are on the syllabus?
No, they're in announcements. They keep changing them.
Okay. All right. Perfect.
Just look on announcements.
That's fine.
Okay. And
Right.
if you, all the LAs are basically are attached to every class. So if you want to go to somebody else's hours, you can just send them an email through Canvas.
Yeah. I just emailed Jad and like asked him about that.
Yeah, it's cool. Just
Yeah.
email them.
Okay. Cool.
So
All
how
right.
many
Thank
people
you.
have left? You're leaving, Joey?
Yeah, I'm heading out right now. I'm gonna go
Okay, take it
for a little
easy.
exercise. Peace. Thank
Sounds
you.
good. Sounds
Have a good day.
All right. You too. Hold on, Chris. That's okay. You can still type stuff even to the LAs. Don't worry. I mean, if I can put you with Jordan if you want. Jordan, is it okay with you if Chris comes to your office after he doesn't have a mic?
Yes.
LAs? Yeah. Jordan will work with you. No worries. So let's see how many people I have left. I have 1, 2, 3, 4. So I have 4 people. And none of them are in your office hours, Leon. So who can stay? What LA can? Does anybody else have office hours right now, by the way, besides Leon? All right, Leon, why don't you go to your office hours? I feel like you'll have some people showing up. Okay? Because I don't want to give you a group since your office hours start in a few minutes. I have one. So how many did I say I have? So I can put who can stay late now into for an LA session.
All right, I'm gonna head out now.
Okay, sounds good, Leon. Take it easy. So who can stay late?
I can stay.
Is that Robert?
Yeah.
Okay, Robert. Well, I'm going to give you everybody. I'm just going to, so Jordan and Gio, you can go, and Robert, you can just have the main screen here.
Okay.
I'm not going to put you in a group. You can just use the main room. How's that?
All right.
Okay, thanks, Robert. Okay, guys, have a
All
good
right.
one.
Thanks, Robert.
Thanks a lot, guys.
Bye, everyone.
All right.
Take care.
See you on Friday.
Okay, bye-bye. Thanks, Chris. So just to say, Robert, Chris is here. You see Spald. You're going to have to open up your chat window or make sure it's open because he doesn't have a mic. He's going to text you things if he has questions, okay?
Okay.
Thanks, Robert. Yeah.
I don't think I have the ability to make a whiteboard. I don't know why.
Okay, let me make sure you do then. Hold on. Let me give you permissions to do everything. I'm going to give you all right. And I'm going to make you a presenter. So now do you have the ability to do everything?
Yeah. Thanks.
Okay. No, my pleasure. Thank you. Have a good one, guys.
All right. Bye.
Thank you.
Thank you. And if you need anything, Jax, I'll be happy to help out.
Thank you so much.
Yeah, check out that Thomas thing. It might be a lot easier.
Yeah, I'm going to call him in the morning.
Okay, sounds good.
Thank you so much.
Okay, bye-bye.
Bye.
Thanks, Chris. You too.
So can we just like go over like one of the questions on the LA for like part 2? Cause like I looked at the front and I answered all in the front. It's just on the back. I'm a little confused.
Yeah.